I want to start today by practicing some of those types of problems like you did see on last night's assignment. So please write down each of these two and find the derivative of each. All right, so for that first one, in its current form, we can't deal with it, so we have to change the form. So what I'm going to do there is I'm going to rewrite my f of x as 6x to the power of 1/2. Now that it's there, I can now apply power rule to it. So that means I can find the derivative. So I go to f prime of x. Keep track of your primes. Make sure they don't appear too early, and make sure they do appear as soon as you're actually taking the derivative, or it can lead you to some trouble. And so for power rule, I'm going to have to multiply the 6 by the 1/2. Well, half of 6 is 3, so that's going to give me 3. And it's going to be times x to the power of 1/2 minus 1. Well, if I take a half and I subtract 1 from it, I end up with a negative 1/2. And this is a fine place to be able to go. We found the derivative, but I do want us to see if we can actually start working on simplifying these a little bit more. So let's go ahead and actually see what this would be simplified. All right, now the first thing I notice when I go to simplify it is that I have a negative in my exponent. As soon as I see that, I know that my answer is going to have a fraction in it. Now, the 3. Does the 3 here go on the top or the bottom of the fraction? On the top, yeah. It does not have the negative exponent attached to it. What does have the negative exponent attached to it is the x. So the x goes in the bottom. Now, I could go ahead and write it as 3 over x to the 1/2, but if I'm cleaning it up, let's clean it up all the way. So instead of it being to the power of 1/2 down here, x to the power of 1/2 is the same as the square root of x. Now, if you want to get extra fancy with it, and no, I'm not worrying about us doing this too much right now, but we could go ahead and rationalize the denominator as well. If you did that, you would have 3 root x over x. That technically would be our most simplified form of this answer. All right, now on to g of x, next to it there. So for g of x, the very first thing I'm going to do again is I'm going to rewrite this so that it looks just like a regular polynomial instead of a quotient. It's not a rational. I want to be able to change that. So this becomes 12x to the negative 3rd. All right, now I can go ahead and apply the power rule. So now I go to the g prime of x. And so I do the 12 times the negative 3, which is negative 36. And it's going to be x to the power of a negative. Make sure you're subtracting from the negative to get the negative 4. And now we're just into the cleanup phase. So the negative 36, that's going to be on the top of my fraction. On the bottom of my fraction, I have x to the negative 4, so that becomes an x to the positive 4 on the bottom. The one last little thing I would do here is that I don't really like that negative sitting just on the top of my fraction, so I'm going to write that out front of the whole fraction. So this would then be a nice simplified version of our answer, negative 36 over x to the 4th. So now having done that, we can very easily do this problem now as well, where we're going to find the slope of the tangent line to this curve at f of 9. And yes, that should be easy to do, because notice we're finding the slope of the tangent line at a specific point. Remember, when you see f of 9, that means x equals 9 in this case. So when x equals 9, what's the slope of the tangent line? What do we use to find the slope of the tangent line? Yeah, derivative. And so when we see slope of tangent line, that's telling us find the derivative. Well, we already did that, right? So let's go ahead and grab that. So f prime of x, we could use any of the forms that we came up with. I'm going to go ahead and go with the 3 over root x, because I think that's going to be the easiest in this case. And so what it's actually asking me to do then is figure out what is f prime of 9. That will be the slope of my tangent line. You might also write it as m for slope, if you wish. In this case, though, I think the f prime of 9 makes the most sense. All right, so that means I'm going to take the 9, and I'm just going to plug that in for x. Nice, easy math here, right? And so that's going to be 3 over 3, which just equals 1. So we could know that if we graphed this equation at x equals 9, it's going to have a slope of 1 at that point. Now then, we do need to talk about some detail-y stuff about our derivatives still. One of those detail-y things is notations. Now this isn't part of your derivative rules, but it is part of your notes. So I would not put this on your derivative rules sheet because these are not rules, but this does go into your general math notes. All of those that you see up there represent derivatives. You want to remember what they are, so write them down. And as you take a look at this list, it seems like a rather exhaustive list, but there's even tons of different ways you could write all of these different things for a derivative, because a lot of these just depend on what we called our original function. And as variable names change, so would our notation. So like prime is the biggest thing out of these top two. But just by writing that prime next to it, I'm saying derivative. That's the most common one that you're going to see, is the prime notation. That's probably the one that you'll end up preferring personally as well. But we still need to be able to use the others as well. So next up, you see all of these are the d over d notation. Now when you see this kind of notation, the d over the d, the top letter after the d, that's always your output variable. So what we normally would call y, you know, like if it's y equals, that's why you see this dy over here. We always put our output variable up top. On the bottom, that's where we do d of our input variable. And so that's why you'll notice that in all of these cases it's over dx, because we're assuming that it's x for our input. But of course, it's not always x, is it? Like, it's very common to see something like d over dt. What that tells me is that this is the derivative with respect to time, or at least t, which is normally time. And so there's lots of different variables that will come up along the way here. Now you notice that in this particular example up here, I didn't write a letter on the top. Well, I then would have to follow it with whatever function it is. So I'd have to then start writing like of t squared or whatever the function was. D over dt needs something with it. If I don't want to write something with it, then I would need to say, okay, I'm finding the derivative of the h function or whatever the function is named with respect to time. And on the bottom, these capital D notations, these are a way to represent derivatives, but they are used much more rarely. So this really is kind of a list in descending order of how often you're going to see these. Prime is the most common. The d over dx notation, that's going to be the next most common, and then you'll hardly ever see the capital D, but we do want you recognizing what it means if it does pop up. Now, why would we want that notation? Because a lot of people are like, why do I need to know some of these other ones? Well, they have some other uses. Like, this is something you already put into your notes, the constant multiple rule, so you don't need to rewrite this down. But I want to illustrate that we had to write it using prime notation like that up there. So notice I had to define the original function up here, and then I would have to say, okay, then when I do that, the derivative will give me this derivative. Instead, notice how I can shorten that using the d over dx notation. I can say that if I'm finding the derivative of some function defined as c times f of x, I can just do c times the derivative of f of x. It's a more efficient notation, at least at times. And we'll even get into some stuff later this year where we'll see that the d over dx notation, specifically even d over dt notation, ends up being super important in allowing us to do some other stuff with these derivatives as well. All right, so to practice our derivatives, here is a function. Please find dy over dx. And so notice this one, it's bringing in our new notation, the dy over dx. So in this case, I would write dy over dx equals. Writing dy over dx is the same thing as writing y prime. But of course, since it said find it that way, I'm sticking with it. And then can I just go ahead and do 20x to the fourth there? No. Remember, we can't do that. In fact, in this case, we have to do something before we go to that dy over dx, right? We have to rewrite this function. Because right now it's a product. It's two polynomials that are being multiplied together. I want to make that just a polynomial. So I do the 4 times the 10 to get 40. I do the x to the 5th times x squared to get x to the 7th. Now I can do dy over dx. And so that's going to give me 280 x to the 6th. And so remember, we got to take a look and simplify these at the start anytime we can. That should then tell you how to handle a problem like this. So please find dy over dx of this function. And again, we're going to start by simplifying the expression that you have. And so in this case, the 3 over 12, that simplifies down to be 1/4. And the x to the 4th over x, that is x cubed. Now, if writing it like that, it does not yet make it clear how to do it, well, that is the same thing as 1/4 times x cubed. And it should then be clear how to find that derivative at that point. And so I'm going to end up doing the 1/4 times the 3. That gives me 3/4. And then my x is going to be 1 lower on the exponent, so that's going to become x squared. And while technically correct, I tend to prefer writing it as 3x squared over 4. I think that's just a little bit of a tidier way to write it. But they both are correct. They both mean the same thing. All right, next problem. Please find f prime of x given this function. And hopefully the first thing you did is multiply it out, because given the original form, we actually can't do it, at least not with our current set of knowledge. But we can multiply it out and use the power rule with that. And so we use power rule on each of those individual terms. And we end up with 42x to the 5th minus 210x squared. Notice there is no third term, because remember, the derivative of the constant is 0. And so we don't need to write plus 0 hanging on the end here. Next up, let's bring those radicals back in. Please find f prime of x with this one. Notice, we'll sometimes be using d over dx notation, sometimes prime notation. You got to be able to be fluid with all of them. And so hopefully, again, the first thing you did was simplify, make it more into a straight polynomial. So 4 times x to the 7/2. If you wrote this as x to the 3.5, that would also be okay. In fact, that would almost be more beneficial to you in the long run in this case. Once you get here, then you can go ahead and find your derivative. All right, and so we'd use our power rule there. We get 14x to the 5/2, which I'm going to go ahead and clean up. 5/2 is the same as x squared times the square root of x, because that's x to the 2.5. And on to the next one. Please find f prime of x of this. Although this one looks different than the ones we've done before, right? So let's take a look at how we would go about taking our first step. And that is, again, to turn it into just straight polynomial, which means getting rid of the division that's going on here. Well, we can do that by saying that since all of this is divided by x squared, that also means that each of those terms is divided by x squared. And so in the big scheme of things, writing it out the longest way first, that means it would be 3x to the 8th over x squared minus 9x to the 5th over x squared plus 5 over x squared. And then we're just going to clean up each of those individual terms. So then this becomes 3x to the 6th minus 9x cubed plus, now that last one is technically simplified, but I need to be able to use power rule on it. So I'm going to write that as 5x to the negative 2. Now we can find our derivative. And so just by applying the power rule, we end up here. And from here, when we talk about cleaning it up, we now have a couple options about what we can do. First of all, we do have that 10x to the negative 3. So I could go ahead and just clean up that part alone and turn this into 18x to the 5th minus 27x squared minus 10 over x cubed. And that's perfectly fine. But let's say you wanted to match the format of the original. Well, that means I'd have to make all of these b over x cubed. So, in case you're curious, you didn't have to do this, but in case you're curious, how could we get there? Well, this 18x to the 5th, I need to make it over x cubed. So then if I think about, okay, I'm putting those 3 back in, that means that would now become an 18x to the 8th over the x cubed. Now again, you don't have to, but seeing how we can. And so then the 27x squared would become 27x to the power of 5. Because then the 5 would cancel out with the 3 to give me that 2. And then just minus 10, because that one's already over x cubed. And so then that would be a good final answer there. All right, I think we're about done for the day, but we do need to take a look at one last concept here. So we're going to see how to deal now with this type of question. And so notice what this question is actually asking us to find. It's saying find the instantaneous rate of change at a equals 2. Instantaneous rate of change is basically just saying how quickly is it changing at this instant, at this one moment. In other words, when we see instantaneous rate of change, it is just a different way of saying slope of the tangent line, which of course means derivative. So this one is also asking us to find derivative. But this concept of the instantaneous rate of change is going to be one that comes back quite a bit throughout the year in different forms, as you'll see. So we're going to find the derivative of this. Well, notice because of this squared over here, that means we first have to multiply that out. So do that first. Now when you square 3a minus 5, remember you're not just squaring 3a and squaring 5. You actually have to do 3a minus 5 times 3a minus 5 and multiply all that out. That's why we do have this minus 30a sitting in the middle there. Don't forget about it. That can lead to a lot of problems if we do. Once we get here, now it's in a nice polynomial form. Now you can use power rule. All right, and so in this case, because it's talking about r of a, I write my derivative as r prime of a. And we end up with 18a minus 30, but we're not done. Because remember what this one asked us to do. It said find the instantaneous rate of change at a equals 2. So now I need to take it one step further and figure out what is r prime of 2. And then when we do that, we should get an answer of 6. That is the instantaneous rate of change at 2. And we'll be seeing later on here how that has all sorts of other meanings and how that can tell us a lot about a real world situation and all that kind of stuff.